Your monatomic gas can move in, let's try this, in 3 dimensions. It has 3 degrees of freedom. It can't rotate, it can't vibrate. And so three degrees of freedom means that each molecule has 3/2 kT energy. Therefore, n moles, let's change that, capital N particles or molecules has your total translational kinetic energy. So that's what we're talking about. This is translational kinetic energy technically. Is 3/2 capital N, which is the total number of molecules, kT. Recall that the heat added to n moles goes like this. And now we just basically need to recall, okay, dKTR. Well, from here, N and K and 3/2 are constant. So a little algebra here. Here's a molar form, here's particle form. It's not a huge change, right? But we know that dq equals dKTR. These are equal. NCV, oops, the dt's go away. Oh, I'll leave them in. 3/2 NK dt. Get rid of the dt's. NCV equals 3/2 capital NK. Boltzmann's constant right here, the K. And we just have to recall, let's see, that Boltzmann's constant is also thought of as the ideal gas constant per mole, per molecule. And so that should be divided by Avogadro's number. And if we put that into our relation here, basically I'm going to solve for C sub V. We get CV equals 3/2 big N over little n. K is now capital R over N sub A. And let's see, what do we recall here? The definition of little n, number of moles, is to take your number of particles and divide it by number of particles per mole. Put that in there. I think you're going to see what happens. We have big N over big N over N sub A, R over N sub A. And there you go. The big N's cancel, the N sub A's cancel once you bring this up to the numerator, and you're left with CV equals 3/2 R. Right? And so in this way, thinking about the possible degrees of freedom of your molecule, in this case for a monatomic gas, that can only translate and have 3 components of velocity and 3 kinetic energies, component kinetic energies, it does a nice job predicting the value we do find, this equipartition of energy theorem. But what about the other degrees of freedom? So we know diatomic gases can translate, so we know they have at least 3 degrees of freedom. But how do we actually count the number of additional degrees of freedom due to rotation? So can translate, right? So there's 3 degrees of freedom. But now we have rotate. The rotation about the x-axis here, on which the molecules lie, you can't excite it. They're really, on the atomic level, you can't even distinguish that it could be rotating like that. There is no real rotation. Right, the energies would have to be ridiculously high to excite that mode. But you can rotate about both this y-axis, this y-symmetry axis, and the z-symmetry axis. So for the diatomic, right, it gets more complicated with the polyatomic. For the diatomic, you have 2 degrees of freedom to rotate. Basically, 2 angular velocities, right? Because I said it was all about kinetic or potential energies. You have omega about the y-axis, you have omega about the z-axis shown here, which means you have rotational kinetic energies. 1/2 omega y, how does that go? 1/2 omega y squared. I need a little moment of inertia in there. You need to know what the moment of inertia of your diatomic molecule is, right? So quadratic kinetic energies is what the equipartition theorem says. So if you have a diatomic molecule, they can rotate in 2 coordinate directions, or have 2 angular velocities, have 2 particular degrees of freedom. So that's now 5 degrees of freedom that a diatomic gas can have. And last, you can have vibrational motion and different modes of oscillation. Here, the modes are going to be pretty straightforward, that they're going to move against one another. They'll both compress in, they'll both extend out. So they're each oscillating a bit about their equilibrium positions, the individual atoms. So here, vibration, it turns out, yes, there's 2 molecules vibrating, but the idea is you take the center of mass coordinates, or you take the coordinates of one atom, and the other one is vibrating relative to it. That also has 2 degrees of freedom, because you have a kinetic energy, vibration of a molecule, of an atom about its equilibrium position. So there's a 1/2 m, we'll call it Vx squared. But remember, it's vibrating about this point. So that's different than translational. This is not translational. It could be translating along that direction as well. Vibrational. And that velocity changes, right? It changes back and forth as it oscillates, like a simple harmonic oscillator, right? And if it is like a simple harmonic oscillator, it has a potential energy term as well, a 1/2 kx squared. So this is quadratic in its velocity as it oscillates back and forth along the x-axis. This is quadratic in its position. And these are energies, so there's 2 more degrees of freedom associated with that. So therefore, diatomic molecules and I'm going to put in parentheses, can have up to 7 degrees of freedom. 3 translational, 2 rotational, 2 vibrational. And if you bought into the derivation I just did for the monatomic gas, that implies that the specific heat is 7/2 R. And this is true at high temperatures. And so that's why the caveat here is, hang on, this is what experiment shows. As temperature increases, rotation. So our temperature increases from 0 degrees Kelvin. Rotation and vibration turn on, or they become possible. But it's a function of temperature. So experiment shows that at temperatures, right, so what is room temperature? Room temperature is about 300 or so. And so at 300, well, let's just go back. Experiment shows that if you start at 0 degrees or very cold and you start measuring the specific heat of a diatomic gas, it's going to be 3/2 R if you're below about 50 Kelvin. And basically, because they can't rotate nor vibrate, you need a higher temperature, more excitation for those modes to get excited. As you increase the temperature, eventually you get up to where the rotation is allowed. So you have 2 more degrees of freedom, 2R over 2 more than 3. So you get 5/2 R. And so this has been measured at room temperature. And this is specific to H2 gas, right? So it depends on your gas. But at room temperature, H2 gas has 5/2 R specific heat. And so usually we will quote 5/2 R when we're talking about room temperature type of processes. But hey, if you're below 50 Kelvin, which is possible, as a gas, which might be tough, H2 will have 3/2 R as its specific heat. But then at very high temperatures, you can excite the vibrational modes. But example, for diatomic hydrogen, this doesn't occur at normal human temperatures. But if you were working at very high temperatures, you'd have to take that into account. And so that's a really interesting aspect of this kind of mechanical model of our molecules. And that modeling them this way, you can theoretically understand how the heat capacities come about. Okay, enough of that. Let's do an example problem. So let's see. Example. First, I'll have to give you some numbers. We have a container of n moles of H2 gas. I will tell you that the specific heat at constant volume of diatomic hydrogen is 20.2 joule per mole degree Kelvin, which should equal our 5/2 R. Calculated out. At the same time, we have the same number of mole of neon gas. We know it takes 300 joules of heat energy to increase the hydrogen's temperature by 2.5 degrees Celsius. Helium is a monatomic gas, and so it has a specific, did I say helium? Boy, oh boy. Neon. Helium is also a monatomic gas, but neon has a specific heat at constant volume of 3/2 R, which is our 12.47 joule per mole degree Kelvin. We know it takes 300 joules of heat energy input to our diatomic hydrogen to increase its temperature by 2.5 degrees Celsius. And the question is, by how many degrees will the neon gas temperature rise? If 300 joules is added. Right, and so the idea is that we take our old expression, not the differential expression, and, well, we basically set this specific, so N, C, V, yeah, okay, so we know that the Q given to H2 of 300 joules is equal to the Q given to the neon, 300 joules. We can express that as number of moles, CV H2, delta T of H2, so I'll give a little H2 there to recall that that is 2.5 degrees, and that's equal to the N specific heat at constant volume of neon and the unknown delta temperature change of neon, right? The mole number cancels, and we can solve for what? Delta T neon. No surprise, it involves the ratio of the specific heat capacities. So there's our delta T of H2 times CV of H2 over CV of neon. Put in the numbers, 2.5 degrees Celsius times H2's 5/2 are, or 20.2. I'll suppress units here because they're all going to cancel, and our 12.47. And if you do the numbers, it comes out to be just about exactly to 4 degrees Celsius. Why did the temperature increase for neon more, almost double, than the temperature increase for diatomic hydrogen? Because hydrogen is diatomic, and the energy can go into things besides translating, which is how temperature is measured, translational kinetic energy. So there's a good quiz question for you answered. Okay. Let's finish up this video with specific heats of solids. This is pretty straightforward, but it's the same idea here. So atoms in a solid are kind of like simple harmonic oscillators in 3 dimensions. At least at normal temperatures. When you get near the melting temperature, the motion is a little more than simple harmonic. It's a little more complex than simple harmonic. It can be very large amplitude just before you melt. So think of an atom sitting there in space, and it's attached to its nearest neighbor up here. They give no direction, so I'm going to go ahead and say there's your z direction, there's your x direction, there's your y direction. So the model in normal conditions is that the intermolecular bonding forces act kind of like springs. And so the idea is that you're going to have vibration in both X, Y, and Z, and that you will have 3 kinetic energies of a simple harmonic oscillator, a 1/2 m Vx squared, a 1/2 m Vy squared, and a 1/2 m Vz squared. Thus, there's 3 degrees of freedom already. But you also have 3 potential energies. And if you take the net electrostatic potential energy that one atom or molecule sees in a solid with respect to all the others, you come up with basically a simple harmonic oscillator potential in 3 dimensions. So, simple harmonic oscillator in 3 dimensions, which acts like 3 one-dimensional simple harmonic oscillators. So you have a 1/2 k x squared, so you'd have to know what the k, and the k has to do with the forces in the x direction. I'm going to assume they're all the same. You have a 1/2 ky squared, and you have a 1/2 kz squared, right? These are 3 more degrees of freedom, right? So solids, generally, basic solids, have 6 total degrees of freedom. And as we found, each molecule or atom will have 1/2 kT for each, so it'll have 3 kT. And as you saw with our little algebraic sleight of hand, if it was 3/2 kT, it was 3/2 R for the specific heat. If it was 7/2 kT for the energy, the degrees of freedom for a diatomic molecule at high temperature, you would have 7/2 R, but 5/2 R at normal temperatures. Here, you're going to have just 3R, right? And that's pretty big. That's on the order of 25 or so. I don't think I have that number right here. Let me calculate it. $24.9. Okay. That will end our lecture.